Yeah, Anja, thank you very much for the invitation and introduction. I'm very happy to present a little bit what we are doing. So my name is Johannes Büchner, and I will present a little bit of current research going on in our institute regarding performance testing in the DSR. We will also start a little bit about what we are doing and where we are located, who we are, kind of. I will also give an outlook in the end. What else are we working on? What research projects are we currently working on? What are, what is the future in our vision, so to say? With me here today is Professor Michael Wistuber. I will just start a little bit presenting myself, introducing myself. So I'm a research associate here at Technische Universität Braunschweig, Braunschweig Pavement Engineering Center, which is our institute's name. I work here now for 6 years. I finished my PhD last year on this topic of mastic testing in the DSR. So that's why I'm basically presenting everything here. In our institute, I'm responsible for, let's say, all the binder testing going on, the binder laboratory, especially the rheological testing. So that's why I'm in big contact with all the EUB3575 points and aspects, so to say. And now I hand over just very shortly to Michael.
Thank you, Johannes. Hello, everybody. Thank you very much, Anja Sørensen, for inviting us for this webinar. I see that there is quite a high number of participants, over 40, which is very nice. I welcome you very much. It is a pleasure for us to speak a little bit about our work, which is almost or mostly done by Johannes Büchner, who is the expert in asphalt binder and asphalt mastic rheology at our institute. But there are, of course, a couple of more people. We are running quite a big set of experiments in the rheological field of binders, which are used for road pavement materials, but also for roofing membranes and others, and other fields. So I'm also very enthusiastic. It's a very nice idea to have this webinar, and I wish you a successful meeting. And now I hand over or hand back to Johannes Büchner. Thank you.
Okay, as mentioned before, I will shortly start introducing our institute. So first off, we are in Braunschweig here, the city of Braunschweig. It's, let's say, central in Germany. It's not really visible on this map because I could not zoom in, but here you can kindly get the idea where we are located. And the city of Braunschweig is also sometimes called Braunschweig in English, is around 250,000 inhabitants, which was founded in 861, so quite an old city. In the Middle Ages, the city was a political and economical center of Central Europe. It's a member of the Hanseatic League, so there was a lot of trade going on. We had lots of half-timbered houses. As you can see, I will take my laser pointer. As you can see here in the corner. But in the World War II, there was a vast devastation. We got a lot of bombs in our city, so almost all of the 1,000 half-timbered houses were destroyed and rebuilt in a kind of post-war construction type. We also have the lion here, which you can see, which is kind of the mascot of our city. It's in the very city center, stands there. And today, the city is an important European location for science and research. And it was the German City of Science 2007. I know it's quite some years ago, but still there's a lot of research institutions which are settled here in our city and the surroundings. We have the Technische Universität Braunschweig. it's officially not a technical university, so the English name is also Technische Universität Braunschweig, so that's why I chose it here, the short form TU Braunschweig. It was founded in 1745 as Collegium Carolinum, and since 1968 it's now a Technische Universität. I gave a small couple of numbers here to get an idea about the profile. Around 18,000 students, around 3,000 graduates and new students every year. We have 3,800 full-time employees and 242 professors. So it's not one of the biggest universities in Germany, but very focused on the technical aspects. The total earnings, these are numbers from last year, 380 million euros for the whole university. Now about our institute, in German it's Institut für Straßenwesen. The English translation was decided to be Braunschweig Pavement Engineering Center, still the short form acronym ISBS. In the 70s we had Professor Arendt, who was the chair of the institute. He worked a lot on the low temperature asphalt performance testing and introduced the TSRST test in the Europe, kind of developed this test, so to say. Then afterwards we had Professor Leutner in the 90s. Both of those already passed away. And so now, since 2008, we have Professor Wistuber as the chair of the institute. In the bottom here, you see some pictures. So these are my colleagues here. We have 10 to 15 scientific employees. So it's one professor, a couple of postdocs, a couple of PhD students. The number varies from time to time, so that's not fixed right now. At the moment we are 11, but next month it changes, so that's why it says 10 to 15. We have 11 laboratory and secretary staff, and then 10 student assistants. And the research focus is completely on asphalt technology. So here I put a small figure which we are using quite often to show a little bit the dependency of the different material components we are looking at. So starting at the binder, looking at the mastic, at the mortar, at the mixture, and the final pavement. I'm sorry if I still have some German slides here. I was not able to translate everything, but I will explain everything so it should be clear. So we are basically looking at all those different phases here, which we see, starting at the binder, looking into the binder, and up to the real pavement. And our range of services in the institute, next to the lectures, include the basic research in building material technology, applied research for construction industry and building materials industry, for associations for the EU, for federal and state, especially new construction methods, building material technologies, maintenance strategies. We have scientific support for innovative construction projects, damage analysis, restoration concepts, testing of building materials during development. And finally, in our laboratory, we do a lot of quality assurance for the state of Lower Saxony Road Construction Administration at an independent test center. And we are also a training center for building material testers. So to give you a small outlook what actually we are working on, we have this laboratory I just mentioned before. A separate road construction laboratory was kind of built and introduced in 1976, and quite some changes during the years where it was located. But now, since 2010, we have a new building, new rooms, and new equipment on total 720 square meters. You can see some pictures here on the right. Our testing equipment includes static dynamic binder testing, binder conditioning, conventional binder testing, but also static and cyclic dynamic asphalt mix testing, conventional asphalt mix tests, aggregate preparation and testing, and assessment of structural and geometric properties of pavements and layers. So here you can see again completely focused on asphalt technology and not including anything else, so to say. So we are not focusing so much on concrete, asphalt concrete, concrete pavements. So now coming back to the title, performance testing of bitumen and mastic in DSR. Why to choose this topic? So I brought this topic here because it's a broad and interesting research area with lots of potential. There's a high interest in the asphalt bitumen community. And there's already a lot of going on in many different other countries and universities on this topic. Currently, it's the main research topic at the ISBS. We have many different research projects connected to this topic. And this is also the basis of recent and future publications. Currently, 3 PhD students and 1 postdoc is involved in this topic. So I'm here, the postdoc, kind of leading and coordinating all the work which is going on in this area. And we are also very much involved in the German and European standardization on this topic. Currently, I'm leading the revision of the EN 16659, the MSCRT test, and the EN 14770, the standard DSR standard. Yeah. This topic is basically, or this topic is based, and this presentation is based on 2 research projects and also my dissertation. So the first research project was carried out between 2017 and 2019. It was a German, Austria, Switzerland cooperation project with the title "A Simplification of Asphalt Performance Testing." The results are available online. I put the link here, and you will get the presentation afterwards, so you can also click and take a look. This research project was also used as the topic for my dissertation. Both of them are in German, so there are some English abstracts included, but everything else is in German. But also my dissertation is available online. So basically, this will be the main part of today's presentation, and the second research project I will introduce later. And now I will just start with a little bit of background. Why are we looking at it? What are the problems we are facing at the moment? As you can see in the title, it already stated performance. So first the question is, what is asphalt performance? So we are looking into 3 different temperature ranges. In the low service temperatures, we have kind of the low temperature behavior, of course, and here we show the typical failure in each of the temperature ranges: low temperature cracking, fatigue cracking at intermediate temperatures, and rutting at high temperatures. And there are different possibilities now how to verify the suitability of a certain asphalt mixture. The first is a conventional test based on empirical volumetric parameters, which is kind of the state where we are in most of the European countries. But there's also the possibility to perform or to carry out performance tests based on physical parameters to ensure good durability of an asphalt pavement and to avoid these failures which we see here in the top. However, this performance testing of asphalt mixture, asphalt performance test in the laboratory is quite complex. As you can see here, we show a little bit what kind of tests are possible: 4-point bending, 2-point bending, 3-point bending, different tension, compression tests, tensile tests, cyclic tests. They all simulate material behavior and try to predict the behavior in the field. However, as mentioned before, this is they require a significant testing effort and very high costs. So they are not really suitable for routine testing, only for very big construction projects or for development of new materials. But we are talking here for one mixture, it's in the range 20 to 30,000 euros to perform the full set of tests. Generally, during the performance testing of asphalt, we are looking at the behavior of the material at low temperatures. We basically look at the stress which build up due to cooling and the shrinkage which is hindered. So here I demonstrate a little bit the 3 different material behaviors in the 3 different temperature ranges. At low temperatures, we see the development of cryogenic stresses in the pavement with decreasing temperature, leading to a failure of the specimen, which is here a crack. And intermediate temperatures, we see a decrease of the stiffness due to continuous loading. So here's the stiffness modulus. We have 3 distinct phases, a quasi-static phase in the second part, and then also the failure phase, where we also see the cracking. And in the high temperature range, we usually look at some kind of deformation of the material due to high loading or to repeated loading. Here we show the plastic deformation, also 3 very distinct phases, which can be determined by different performance tests. And also here we have kind of the 3rd failure phase, where we see rutting and kind of destruction of the material behavior. Now, also in the title, asphalt mastic, what is mastic? Now going over to the material we are looking at. Here you see a figure representing schematically the asphalt. We have some air voids, different aggregate sizes, and the binder. And the term asphalt mastic is not clearly defined somewhere. It's quite different in Europe and in the US, for example, but also in Germany, we have some problems with this term because some people use it different than others. So here in our study and in our institute, we defined asphalt mastic as the composite of binder and filler including all the aggregates smaller than 36 micrometers. Asphalt mastic is kind of the composite, as said before, and there's a physical-chemical interaction of both components. And actually, this composite acts as a glue in the asphalt mixture because there's no differentiation possible between binder and filler in the actual mixture. It's an homogeneous composite. The volumetric composition and interaction of the both components are essential for performance properties and durability, but there are no established test methods for asphalt mastic. So in the Vegas project, which I'm now presenting, we basically looked at simplification of performance testing, as you see before, but performing the test on mastic and developing new mastic tests. Using the dynamic stereometer, which is a universal rheological test instrument to measure rheological material properties, so deformation and creep behavior. It's a very versatile instrument. We can do the loading and shear, either static loading and rotation or dynamic cyclic loading and oscillation. And there is a possibility to perform mastic testing in the DSR, and many researchers already started to perform such tests and to publish such tests, especially in Europe, but also in the US, for example, and also in other countries. DSR is the most promising test instrument because it allows testing in the full in-service temperature range, so from -40 to +90, with a great variability and applicability of the chosen test parameters. When looking at the difference between binder and mastic, this is what I show here. You can see the complex shear modulus on the y-axis and the temperature on the x-axis. And I just demonstrated here the behavior of the binder and the change in stiffness with temperature. And we see we are here at 1 gigapascal at -30, so very stiff material behavior, going down to 0.1 kilopascal at very high temperatures. So you see the very extreme temperature dependent behavior. And we also see the same behavior for an asphalt mastic, which is just a mixture of 50% of the same binder, 50-70, and 50% of limestone filler. It's actually 6 times more stiff compared to the bitumen, but still almost the same behavior. Now, when looking into the standards and the recommendations, there are, depending on the stiffness and the shear modulus, recommendations which geometries to use in the DSR. So basically, the parallel plate geometries is used, and the recommended range for 25 millimeters here, 1 kilopascal to 100. Then from 100 kilopascal to 10 megapascal, it's the 8 millimeter geometry, 8 millimeter in diameter. And now just recently introduced into the current draft of the standard, the 4 millimeter geometry for this very low temperatures, 10 megapascal to 1 gigapascal. And you can see here, based on the stiffness curves, it's roughly this temperature ranges which are suitable for the different geometries, minus 20 to 10 for the 4 millimeter, 10 to 40 for 8 millimeter, and 40 to 70 for 25 millimeters. It changes a little bit depending on the stiffness. For mastic, might need a little bit higher temperatures, but basically that's the background why we are using different geometries actually in the different temperature ranges, and divide all the testing in different temperature ranges. Now coming to the objective, I mentioned before already, within this research project Vegas and within my dissertation, the objective was to develop a practical testing system in the DSR to evaluate significant material properties of asphalt mastic and bitumen. I added here because we currently also look at the bitumen itself, not only the composite. The whole testing system should be oriented on the performance test of asphalt mixtures. It should consider the entire relevant temperature range, and it should give meaningful and easy interpretable material parameters. Additionally, it should be a fast and qualitative material evaluation and possibly also a specification. With this testing system, we are also looking at the correlation of asphalt mastic and asphalt mixture performance in order to analyze possible simplification or replacement of performance test on asphalt mixture scale, and maybe also prediction of asphalt mixture properties based on simplified DSR measurements. The methodology here was that we looked at 18 different asphalt mixture AC11 variants, which were produced in our lab. We varied the asphalt binder type, included 4 different types and 4 different manufacturers, as you can see here in the middle. We also varied the aggregate type. Since this was the German, Austria, Switzerland cooperation project, we used some aggregates from Germany, from Austria, and from Switzerland to compare the behavior of this different aggregates here. For each of the for each of the mixtures, we prepared the mixtures, we performed mixture tests, but we also looked at the mastic. So we created for each of the variants the corresponding mastics corresponding to the mix design. So we took the fillers from the gabbro and from the limestone and added this with the 5070. We also took the fillers here from the porphyr and from the limestone from Austria. So basically, we made an image of the asphalt mixture and created similar and identical asphalt mastic corresponding to each of the 18 variants here. Now, this is the testing methodology we were applying, separating the temperature range in low, intermediate, and high temperatures. And the key pavement failure here was in low temperature cracking, intermediate temperature fatigue, and high temperature permanent deformation. Now we looked at performance tests, fatigue, creep, relaxation testing. For the asphalt mixture, we applied standardized and well-known tests where we had a lot of experience in our lab. So here we used the thermal stress restraint specimen test. We used the uniaxial tension compression test and the cyclic compression test here according to European standard, German standard, or some test here which was developed in our institute. For the mastic testing, we used different geometries, so to say, according to the expected stiffness of the material in the low, intermediate, and high temperature range, and quite looked at what is the predominant material behavior which is important, and tried to develop suitable tests for the different temperature ranges. Here you can see the overview of the asphalt mastic tests which we are performed and developed after consideration of the literature, consideration of the pavement, of the performance tests of the mixture. So we use different test temperatures at each of the tests, for each of the tests. For the relaxation test, we had a constant shear deformation of 0.1%. For fatigue test, we use oscillation test with increasing shear stress. For the creep test, we use a constant shear stress. So kind of using the broad variety of the DSR for application. I will demonstrate the 3 different tests in the next slides. The test duration is already included here. You can see we tried to reduce the testing time as much as possible. So testing time 60 minutes, 120 minutes, 120 minutes. Actually, now we reduced this already with further development. So the whole test system can be applied within 1 day to determine the performance behavior of an asphalt mastic. I will start with the relaxation test at low temperatures. I can also give you more information afterwards, but I tried to put as much information as possible in this presentation. So that's why I not go too much into detail how each of the tests works. So here you just see the result of this relaxation test, where we applied a constant shear strain of 0.1% for 60 minutes. We measure the shear stress, which reaches a maximum value here in the beginning of the test, and then constantly decreases due to relaxation within the material. And we finally use the proportional stress relaxation, so the proportion of the stress which is relaxed from the maximum stress, as an indicator for resistance against low temperature cracking. Intermediate temperature range, we tried a lot and used tests which are available, but we're quite unhappy. So this is what we came up with. We use a constant shear stress test, but the shear stress, as you can see here, is stepwise increased during the test in order to allow an accelerated fatigue test. This is one of the main issues with fatigue tests. They require a lot of time. And we don't have so much time, and we don't want to wait 1 day for one test result. So this is our solution, our proposed solution here from this research project. From this stepwise increase of the shear stress, we can measure the shear modulus. You can see here it's quite linearly decreasing in a logarithmic scale, and then finally reaching a failure point here after around 48,000 load cycles. We evaluated this test with the fatigue criterion according to Rho. This is what you can see here. We look at the energy ratio, determine the maximum point of the energy ratio, which is then the number of load cycles to reach this maximum, is the result of the test as an indicator for resistance to fatigue cracking. Here you can already see we required to use a polynomial regression, since due to our stepwise increase, we can also see these small peaks here, which make it difficult to actually determine the maximum. We already have a solution for this as well, but this is the status from 1 year ago, which was the result of this research project. For the creep test, we also looked at the MSc-RT, which is available in the European standard, but we also looked at the extended creep test, where we extended the creep phase to 1 hour. You can see here creep phase of 1 hour with a constant shear stress of 0.5 kilopascal. We added a recovery phase of 1 hour with a shear stress of 0, and we can clearly determine the shear strain, which evolves here, kind of reaches a quasi-linear phase here, constant creep, and then we can already see the recovery here in the second part. And why we extended this time so much is we wanted to acquire this linear behavior, what we see here, this linear creep, this constant creep. And actually, we look at the creep rate in this range of constant creep, and this creep rate is a rheological parameter, which is an indicator for resistance to rutting in our test methodology. For the performance testing of the asphalt mixtures, the corresponding asphalt mixtures, as said before, we used the thermal stress restraint specimen test. You can see here on the left-hand picture, a kind of tension compression test in the middle for fatigue testing, and cyclic compression test here, which is damp penetration test, actually, on the right-hand side. Now, for each of the different temperature ranges, we have a specific material property which we are looking at, and now we can compare the performance parameters which we defined and which we determined. So in the low temperature range, we have the proportional stress relaxation, the performance parameter, and which can compare to the cryogenic stress of the asphalt mixture. In the intermediate temperature range, we have the load cycles until failure in both for both material scales. And in the high temperature range, we look at the creep rate. So I did not go into detail how to determine these values for the mixture, but they can be determined from this performance test set before. So also the creep rate is a quasi-static constant creep of the material. The load cycles are determined with the energy ratio, and the cryogenic stress is just determined from the curve of the cryogenic stress at the specific temperatures which we used here. Now, maybe I go into detail a little bit about why we not only included static temperatures here, but also shear modulus temperatures, since we wanted to analyze the applicability of those temperatures for performance tests. Now, after this research, and also in the next research project, we kindly slightly varied everything, but this was kind of the first idea that this low temperature shear modulus temperature of 400 megapascal is quite in the range -5 to -20 degrees, which is the critical temperature range for each of the binders used. In the intermediate temperature range, this 15 megapascal is also in the range 15 degrees, and in the high temperature range, this is the value which we already introduced into the European standard as an shear modulus temperature. So testing each material at a specific temperature where the binder has the same stiffness, the same shear modulus. Now, I'm just briefly demonstrating the results of this research project, where we do a direct correlation between the asphalt mastic and the asphalt mixture behavior. So we saw before, for each temperature range, we have two material parameters, and they are here now displayed. One is on the x-axis, the other on the y-axis. So we can see here the stress relaxation of the asphalt mastic from the DSR. We can see on the y-axis the cryogenic stress from the asphalt mixture. So first off, we can see a broad range here. The behavior goes from 75% relaxation capability to 98%. So it's a clear differentiation based on the temperature. So at lower temperatures here, -25, the relaxation is in the range 75 to 85, and in the, let's say, higher temperature range, here going to up to -12, minus is missing here, going up to, let's say, 98% Actually, it's 96% of relaxation. Now we see very similar behavior on the asphalt mixture. So at low temperatures, we have very high cryogenic stresses in the mixture, and at higher temperatures, we have lower cryogenic stresses. And actually, we found a linear correlation between the stress relaxation from DSR and this cryogenic stress, where we also see the influence of the binder. So the softer binders, which are included here, so the legend is quite large since it's 18 different material variants. So the softest binder here was the 7100, which was tested with the gabbro, the porphyry, and the silicate. And all of those are kind of in the, for each of the temperatures in the good performing area, performing better than the others. Cryogenic stress is lower as expected, and stress relaxation is higher as expected. So a clear differentiation based on the binder, and since we did not test the binder, also the influence of the filler, which is already included here, and which shows clearly this correlation between mastic behavior influencing the low temperature performance of the mixture. The same was done for intermediate temperature range for fatigue testing. So here on the y-axis, you see the load cycles determined in the DSR for the mastic, and on the y-axis, the load cycles to failure for the mixture. And also here, it's a linear correlation. Low fatigue resistance is when the mastic has low fatigue resistance, also the mixture has low fatigue resistance. And at 20 degrees C, the low fatigue resistance, the fatigue resistance is lower compared to the lower temperature range here, where we have a higher fatigue resistance. The material is more stiff. Here you can see again this equilibrium modulus temperatures. It's in the intermediate range, 14 to 18 degrees C for each of the binder, kind of overlapping both of those here, but still again with the differentiation between different materials, we can see which material have the highest resistance to fatigue cracking, so to say, and materials with lower cracking. We see again that softer materials, the 7100 here, have the lowest resistance, the lowest load cycles. So again, a clear differentiation, characterization is possible, and also a correlation between both scales, which we are looking at. Then finally, also for the high temperature range, which means here we looked at temperatures 47 to 59. So softer binders were tested at lower temperatures, harder binders were tested at higher temperatures in order to show or to see the significance of the binder stiffness. Here we see creep rate on the x-axis from the DSR and creep rate on the mixture from the cyclic compression test on the y-axis. Actually, you see here the x-axis is displayed in logarithmic scale, since we found that the mastic differentiation is much bigger than the mixture. So you can see here the polymer modified binders, which are here the 45, 80, 65, for example, but also the 25, 55, 55 here. They have very low creep rates in the DSR, while they also have low creep rates at the mixture, but here they are quite zero, almost zero, so to say, compared to the unmodified binders, which are here on the top, and the soft, especially the soft binders here, the 7100 is here in the very corner, but also the 5070 is here in the top. You see they have a creep rate in the range of 5 to 10% per second, and this corresponds very well with the high creep rates this material induced in the asphalt mixture. So overall, conclusions for this project Vegas, it's a novel performance test methodology for asphalt mastic. There are three main outcomes. That first one is that there's a differentiation and characterization of asphalt mastic possible. We can clearly see the influence of different binders, different fillers, and their influence on the mastic. We found a correlation of the material behavior for asphalt mastic and for asphalt mixture between both scales here. And possibly also a prediction of asphalt mixture properties by only looking at the mastic, since there was a clear correlation between those results. Now, coming up to the second research project, which was a follow-up project here. The English title or translated title is Development of a Methodology for the Evaluation of Binder and Mastic Properties in Asphalt Road Construction. It was called BITQ, running from 2019 to 2021, and it was funded by a consortium of 6 German asphalt construction companies, since they wanted to have some solution in order to, or they wanted to have a new methodology and to see what can they apply, a practical methodology. This was also the motivation of this project, to develop a test methodology for practical application, a fast and simple test, easy interpretable, applicable for plant-produced mixtures, since before we only looked at laboratory-produced mixtures, and also including a variety of different asphalt mixture types, and including RAP, since before we only included one mixture type. So also within this project, we kind of advanced the test methods for application for bitumen, so not only asphalt mastic testing, but also asphalt binder testing. And in this project, it was also included that we trained the company employees to perform the tests, which we developed in our institute. And finally, we performed a comparative study between the 6 companies and our lab to see if we get the same results or not, and first indications of the precision of the new and novel test methods. I just go briefly into the results of the test. We had 6 mixture types, so each of the companies provided one mixture type, and they also provided no components for each mixture. So you can see here we had, this is the German classification, stone mastic asphalt and asphalt concrete, most of them for surface course, one binder course, different bitumen types, unmodified and modified, different RAP content, so 3 materials with RAP and 3 without RAPs, different additives, here we some fibers, adhesive agents, and fillers. Actually, all those components which we need for the mastic were provided corresponding to the mixture, so we were able to fabricate the asphalt mastic from individual components for each of the mixtures according to the mix design. So this is now the kind of the recipe of the 6 mastic variants which we created accordingly to the asphalt mix or asphalt mixtures, asphalt mix variants. Now we did exactly the same as before. We slightly varied the test temperatures, but the overall test methodology is the same. So I can just present the same results as before in the correlation analysis. In the background here, you can see the gray points, which were the results from the previous research project. And now in color, you can see overlaid the new results from the 6 plant-produced mixtures, where we produced the mastic correspondingly in our lab and tested the plant-produced mixtures also the performance, carried out the performance test accordingly. And here we can see very nicely the fit of this linear regression is very solid. So again, you can see also the number here of individual experiments. So there are 270 individual experiments, since we have a lot of replicates here already in the background displayed to check really the outcome, if it's really solid or not. The regression coefficient here was 0.91 for this data, so we were quite happy to see that the whole methodology also works for this plant-reduced mixtures. For fatigue testing, the same applies here. We checked now only two different test temperatures, 10 and 20 degrees. We can see the results from 10 degrees here are again overlaid on the results from previous research project. All 6 materials here can be differentiated. So for example, you can see the variant number 1 is the dark blue one, has the lowest fatigue load cycles, and actually this number 1 was the softest binder. Now when I go back, you can see the number 1 was only with the 7100 no rub content. So this was kind of the worst case for it's good for the low temperature behavior. You can see that here in the low temperature relaxation has a relaxation capability here at -10 degree. I have to check. The circle is -15 of 98%. So almost all stresses can be relaxed by the soft binders, but we don't have such a high resistance to fatigue cracking, what you can see here with very low load cycles. We can also see the more stiffer materials here and more advanced materials which have higher resistance to fatigue. Here in the top, we had the second test temperature, which was 10 degrees C. Actually, here the correlation was not so clear because we have a lot of variation in the test results. The repeatability is very poor. We cannot really see here. We did not really understand why some of the points are here or there, but overall, we can still assume that there is a linear correlation between the mastic on the y-axis and the mixture performance on the x. Mastic on the x and mixture on the y. Sorry for the confusion. Then for the creep testing, we had some very interesting findings. So again, you can see here the gray data points in the background. We overlaid the colored points for the 6 new mixture variants, and 4 of the mixture variants kind of follow this trend, which we expected. So this is a logarithmic trend, linear scale for the asphalt, logarithmic scale for the mixture. However, there were 2 mixture types and 2 mastic types, correspondingly the number 3 and the number 6, which did not follow our expected trend and were kind of confusing for us in the beginning. But when we analyzed the composition of each material and each mixture, we identified that these 2 materials had a very high content of natural sand in the mixture. And of course, we cannot include or see the effect of sand in the mastic, because mastic only includes the filler, the very small particles. And if there are higher particles which are round, so to say, and have influence the creep behavior of the mixture more than it influences the creep behavior on the mastic level. So all the other materials which we see here were created with crushed sand. So here's the limitation of this correlation, is that we have to use a similar type of sand, because the sand affects this high temperature performance of the asphalt to a huge extent. Here actually, just to finalize this, we used 2 different test temperatures, 50 and 70. So we did not use this EQG modulus temperature anymore, because we found that it does not give any benefit. It's actually more complicated to analyze and evaluate the results, since there's a double effect. We have the effect of the temperature and then the test results. So it's easier to compare specific materials as a fixed temperatures than compare them at a varying temperature. Now, from all the results we gathered, we looked at forecast functions to actually forecast the behavior of the mixture from the mastic testing. I just copied them here. So you can see here for low temperature, we have 78 different material variants, because we also had some extended student thesis work, which were also included here. We have a linear fit around 0.9. We have here 66 different materials, linear fit 0.8. So it's not as good as for the low temperature behavior, since we have here some points which are quite far away from our linear regression, but still we can see a clear trend and correlation. And for the high temperature range, here it's not as perfect, but we have to keep in mind this is also a logarithmic scale. So we used an exponential fit here. Regression coefficient was 0.78. And we only included crushed sand variants here. So the ones which with natural sand were not used, since we can only forecast with our mastic test the performance of a mixture with crushed sand. Maybe there might be some coefficients to correct this natural sand, but we are still continuing our work here. We also extended the performance test in the DSR on the binder level, just to compare also the effect of the binder. We were slightly varied. For low temperature, we used identical test setup. For the fatigue test, we slightly reduced the shear stress increase, so this step experiment, and also for the creep test, we reduced the shear stress. We also reduced the test duration here. Unfortunately, I forgot to change it, so it's only 10 minutes. I have not prepared any results of the binder, because it's just very recent that we also included the binder testing. But what the results show is that it might be enough to check only the asphalt binder. The filler does not have such a big influence when you look at good fillers. So in our case, we had very much experience with all the fillers. These are empirical experience that these fillers will work also very well in practical on site. So this is still on the work. There are already some publications, but still working on that. So now I'm coming already to the summary and outlook of the whole topic. So we have a quick, easy and plausible testing methodology for asphalt mastic in the DSR, which is also applicable for plant-produced mixtures with RAP. So because actually here we had to extract the components for the RAP and to include them in our mastic. The identified material parameters are easy interpretable and conclusive, so you know exactly what is a preferable material behavior and what is less preferable. There's a clear differentiation and characterization of asphalt mastic. We have a correlation between mastic and mixture performance. Asphalt binder is the most dominant influence factor here, so that's why we now continue to look more on the binder level. The prediction, or this whole methodology, allows prediction of asphalt mixture properties with quick and cheap DSR measurements, only using one test instrument. And that's also one of the big differences here to the asphalt performance testing, where you have very different instruments and test methodologies. Here you can just apply everything on one instrument. Actually, the test methodology was successfully implemented at the companies, so they were kind of surprised and happy that they can try this with their own materials. We carried out an interlaboratory study, which was satisfactory. It was not perfect, but we didn't expect that because the companies tested first time with mastic. We also compared the applicability for two different rheometer types from Anton Power and Netsch. And repeatability was approximately 15%, reproducibility 30%. So that's also the values which are in the European standard for general DSR testing. Might be better in the future when there's more experience, but this is the current state of this testing. So now there are mainly three possible applications of this methodology. The first is quick and meaningful quality assurance. So you can check your materials which you receive before you prepare and create mixtures. You can develop new and optimized mix designs based on your available components. And one of the major points here, replacement of complex performance tests on mixture level. Since we see the clear correlation, it might not be necessary to perform this expensive test in any case, maybe for some cases, but not on a routine scale. All this allows an extended insight into occurring failure phenomena and might be a tool for increasing the durability of our placements in the future when choosing correct and optimized materials and compositions. The outlook is that we are looking at real scale application, also working together with the companies to look how is the change with aging during the mixture, during the mixing and compaction and after compaction, maybe can be applied there or not, to look at different binder additives and their influence on the test results, to identify parameter limits to ensure good quality, because now we only have correlations, but we don't know where's the limit. Maybe we need at least 90% of relaxation in order to avoid any cracking at low temperatures. So this is something we will continue to work on, and I will already present to you in the next slides a little bit what are the projects and our funding for this. Actually, there are two important projects to mention at this stage, which are from the Federal Highway Research Institute in Germany, the BAST. Maybe most of you might know or heard of them. We internally called the projects BECIBIT and REMAS. The first one is, both are in German, but I translated the title here for you. The first one is Investigations into the Characterization of Bitumen. Started in February this year and runs for 2 years. And here we are actually working on looking at different test sites, look at what are the optimal rheological parameters to characterize the binder, where are the limits, what happens during the aging, during the mixing, during the compaction, after a couple of years maybe, in order to start identifying some limits and some optimal parameters for standardization maybe in the future. The second project here is optimization of methods for testing filler bitumen composites. Here it says asphalt mortar in the title. We did not choose this title, but actually it's asphalt mastic and not mortar in the dynamic shear rheometer. So here we kind of screen what is available on mastic tests in the DSR, because it's not only what we're doing, there are a lot of other people also doing, identifying the most suitable test methods, and kind of introducing new standards, how to test mastic on a standardized way, very simple in a dynamic shear rheometer. So we can start better comparing the results from different laboratories, which is quite difficult at the moment because everyone is doing their individual results and testing. So the second project just started in April this year, also runs for 2 years. So this is the funding into more advanced testing and development of the methods, advancements, because we have already a lot of experience now with 4 or 5 years of testing. I know exactly where we have to start and where we have to look at. So I'm really looking forward to the results here. We already have very first results, and you might see some more presentations, publications, and so on these two topics in the future. There are already 4 English publications on the topic, which I just demonstrated before. If you're interested, one publication about low temperature properties, one for the high temperature properties, one for the fatigue properties, and one including all the 3 different temperature ranges, since most of the documents are in German, so this is what we have in English for the moment, but we will extend this list in the future for sure, and already working on many different publications here. Now, this is it for the whole topic of performance testing of bitumen and mastic in the DSR. And now I'm just having 2 or 3 more slides showing you other fields of research activity. As said before, this was our main research, but we do a lot of different things as well. So these are our current research projects, which we are working on. Again, we have 3 other projects from the Federal Highway Research Institute. One of them is called eCharge, where we look at inductive dynamic charging of electric vehicles. We have one pairing where we look at the extraction of binder from the mixture with tetrachloroethene. This is not standardized in Germany, so that's why we start using a standardized procedure here and determine the precision of the extraction using pair. We also look at ecological and sustainability environmental facts here. The project EcoPost is the sustainability potential in road construction with a focus on greenhouse gas emissions, energy demand, and resource conservation. All of those projects here are worked on in German. So we don't, actually, I think we only have German projects at the moment. Then we have the Lane Charge project, which is quite similar to the eCharge project, where we look at innovations for sustainable mobility, semi-dynamic inductive charging of e-vehicles. So very similar title, but looking at from a different perspective here. And finally, we have a project called MARS from the Road and Transportation Research Association in Germany for multiple recycling of asphalt and road construction, which is a very important topic in Germany at the moment, since we already recycled our pavement once and twice. And now is the question, where are we going in the future? What are the problems and issues with multiple recycling and the possible solutions? On top of the research projects, we also have other fields of activity on the topic bitumen and bituminous materials. Here we don't have any funding at the moment, but we had funding in the past, or we are applying for some funding at the moment, just giving you an idea what else is going on in our lab. So most importantly, of course, development of new rheological test methods. So here we worked a lot on 3-point banding test in the DSR using a linear drive, determination of the Poisson ratio of binder, kind of very scientific questions here, but using a very scientific instrument, so to say. So not for practical application, but just to generate some new knowledge here. We recently started a lot with alternative materials, so characterization of bituminous roofing membranes, bituminous membranes waste to see what's the aging of the bitumen in the membranes, bituminous damp proofs, bituminous sealants. So kind of border between pavements and buildings. The interlocking idea here, apply the test methods which we have to other industries. There's a lot of interest in the industry. We work together with the roofing membrane manufacturer. He's very interested. So there's a lot going on this topic, also on recycling of this bituminous membranes in general. Then we look a lot on different additives, of course, testing and evaluating different additives for bitumen and road construction, warm mix additives, especially waxes, polymers, bio-based binders, also very important topic, rejuvenators. We also have some publications on these topics. And then extraction and recovery of bitumen and mastic is also part of our research activity. I just presented before we work on this pair extraction, but previously we also looked at novel solvents. So here we looked at methyl octanoate for extracting bitumen, since there are a lot of health issues with the current solvents we have available. and we need to find solutions here. And we work on mechanical extraction, so without the need of solvent, trying to get the mastic, so get the filler bitumen composite from the mixture, kind of by breaking big particles into smaller particles and creating some material which we can test in the DSR. And the last thing I would like to mention here are non-destructive test methods. So here, acoustic resonance analysis, we work on that also on binder mastic mixture to see, can we test the shear modulus and phase angle just from this acoustic analysis. With that, I'm coming to the end, and I'm happy to answer any questions, and I'm happy for any remarks from you, from the audience. Thank you very much for your interest, and I hope you get a good insight in what we are doing at the moment and what are the outcomes and what will be done in the future.